So this is problem number 34 from your textbook. It describes pushing a crate up a frictionless ramp at an angle of 27 degrees with a horizontal force of F. So we know what our mass of this particular crate is. Ours happens to be 100 kilograms, and the angle at which it's going up the ramp is equal to 27 degrees. It asks us to determine the magnitude of F. So what's the magnitude of F? And it also asks us to determine the magnitude of the force on the crate from the ramp. So the force on the crate by the ramp. All right, those are the things that we're going to be looking for in this problem. All right, so it may seem very tricky. I mean, the thing that most often happens when people look at a problem like this, they say, okay, well, what equation do I need to use? And they go looking for some type of ramp equation or something of that type. What is more often the case than not for a lot of physics problems like this is there just simply doesn't exist a single equation that you can use that looks like it's specific for this context. The equation that you need to be able to, the principle you need to be able to apply is Newton's second law, that the net force acting on this object is going to be equal to mass times the acceleration. And I should be a little more, sorry, I forgot to mention something about the problem. What it says is that the crate is sliding up at a constant speed. And that is probably more than anything else the big hint to us that we should be using Newton's second law. Because we know that if it's at constant speed, so there's actually a velocity here. This is some constant speed that it's moving up. So it's some positive value, we assume, but it's moving up at constant speed, which means if it's constant, what's that tell us about the acceleration? Constant speed means that the change in the velocity with respect to time is going to be equal to zero, because the change in velocity is zero. So there's no acceleration, right? So we end up with the net force is equal to zero, which someone might say, oh, well, that's really Newton's first law. And it kind of is, but we're getting information from the problem in order to simplify it down to the fact that we know that the net forces acting on this object have to be equal to zero. So it can be kind of problematic if you're like, oh, it's moving, and so there has to be a push. And that's a very common idea, that there has to be a push for every movement. But this is already moving at constant speed, and so physically we apply the same principles that we would if it were standing still, that the net forces are going to be equal to zero. Now we need to do the work of identifying all the forces. We know that there's this force F that's pushing on it, kind of an external force, but what other forces are applying? The problem itself told us that there was no frictional force, so we can ignore frictional forces in this particular case. There are other forces that are also pushing on the ramp, though. We know that there is a gravitational force acting on, I shouldn't say on the ramp, on the crate. We know that there's a gravitational force. This is the force on the crate by the Earth that's acting in a direction that is vertically downward. Okay? We also know, and the problem even kind of gave us a little bit of help on this one by asking for us to identify what the force on the crate by the ramp is. Well, there is a force on the crate by the ramp, and that force acts perpendicular to the surface. That's the normal, that's what we call the normal force, because it acts normal, which is the fancy math way of saying perpendicular, to the surface. It doesn't necessarily act vertically upward. It's not the Newton's third law pair to the force on the crate by the Earth. This is a very different force. This is the force on the crate by the ramp. Now, if we knew exactly how long each of these vectors were, we could do the same thing. Recall that this is a velocity vector, not a force vector, that one that I drew there. We could sum all these up. We do know that the sum of these three forces, the F, plus what we'll call F of C by E, right? The force on the crate by the Earth, and the force on the crate by the ramp, these should sum up to 0 because we know the vector sum of all the forces acting on this crate have to equal 0. So pictorially, this is what it should look like, right? And that's pretty much represented what we have with the way that our vectors are drawn. It's not perfect, but that's kind of the sense of what we need to be able to identify. So in the next video, we're going to talk a little bit more about how we pull these together.